So everything is there, but nice. Thank you. Yep, streams are up. I should go to Twitch and get the pop out the chat window. Right. Yep, looks good. Right. Maybe I should listen in on the audio ones and to see if everything's working. Yeah, even Twitch has very low latency connection. Cool. All right. So today we will talk about this contraption that we have in here. This is a Raspberry Pi but modified. I will do a side-by-side comparison, but before that I needed to wrap up something that I have on my desk, and there's something interesting going on in here. I just wanted to talk about it and get it off my chest. There's something funky, there's a funny business in here that is very hard to explain in a general context. So in a stream, in a time when nobody's specifically watching, it is actually maybe this is the time when I just talk about it and move forward. I'll have a video bite of what am I talking about in here. This is a Latte Panda Mu board, and this Latte Panda Mu board, this has a compute module in here, and this is the carrier board side of things, right? So if you're uninitiated, this is the Intel in older like N series chipset based a board. So x86, not a like ARM architecture like Raspberry Pis and all. So this one has a lot going for it. You can just pop in Linux image or Windows image and install anything. It does not need to be specifically made for this board or anything. So there's a lot of versatility. You can run it as a home server or stuff. And the board design, design of this board is open source. You can actually go visit Latte Panda's website and look at it. Let me quickly show you what do I mean by that. So let's say on GitHub. Okay, let me turn on the thing. So if you see, this is Team Latte Panda, as Latte Panda Mu repository, and here you have all the details about this project. And if you go into the electricals examples, this light carrier board, you have the entire KiCad design files and everything, like schematic and all. You can even see the schematic from over here that talks about all the electrical connections and all that it has implemented. Anyway, so this is too much into the weeds. That's not really the point I'm trying to make here. The point that I am trying to make here is, in this design there's a little bit of a mess up, and I had to figure that part out, and then made some little bit of a modification. If you can see in here, this is a USB-C power input. So what ended up happening is, I wanted to use this board with a regular, give me a sec, let me bring, so I wanted to use this board with something like this. This is a PCIe NVMe adapter. So you have the NVMe drive in here, which connects hooked over a PCIe lane, so you can just pop it in over here, connect it like this, and then this should work. However, it doesn't. So the first thing I tried to figure out why it doesn't. The answer was kind of obvious that, okay, in order to make PCIe work, you would need 12 volt power input. So now in more details is that, okay, there are two different, ignore this for a bit. So there are two different power inputs, like one is USB-C and one is barrel jack, this DC barrel jack, right? So if you use this USB-C, then this PCIe does not get 12 volt power. This is not supported. Why? Because this input is only supports 15 volt 3 amps. It's written 15 volt, but USB-C PD also dictates that 15 volt is at 3 amp. So that means 45 watts of power, 15 times 3. And this PCIe specs need 75 volt, so watts of power to be delivered. 75 or 72, I'm not entirely certain, but it's 70 plus. And in order to support that, you would need a lot more current here, like 5 amps or more. Because this is not possible, they added this barrel jack and ensured this barrel jack has a high current capacity, and it works with this lane, and this also has a voltage limit, like if it can accept up to 19 volt, like 20 volt, like normal laptop DC barrel jacks. So you can put it in a high power connector, but unless it's within a very certain range, 11 to 13, like almost 13.5 volt, like within 12 volt range, plus or minus, it would not give power. It has a comparator in the schematic. It would not serve power to the PCIe lane. The challenge with that situation is that even though you can power the board with this PCIe connection is 4-lane PCIe, it's half the entire bandwidth, but using it, operating it is really difficult. It is so challenging to make it work. You need to basically walk a tightrope of all those different confusing setup, and even if you end up giving it a 12 volt, and at 12 volt to go up to like 75 watts, you're basically handling like 6 or 7 amps of current with this. Because actually the more than that, because not only that you need to power the PCIe lane, which is in itself is 70 plus watts. This module itself is also 36 watts, like maximum TDP. So, and there are other peripherals are there as well. So overall board power becomes like 125 watts. So if you are powering it from a 12.5 volt adapter, you would need 10 amps of current. This whole thing is impractical. Most of the time you're not actually using a PCIe that takes that much of current, so trying to comply with that is a fool's errand. But let's leave that that's besides the point now. I was like, okay, fine, I will make it work. So what I ended up doing is that I tried to get a like barrel jack like this, and add a normal buck converter or boost converter, something that can serve 12 volt, so that I can add it here. This module or any other module like this, like a wireless module like this, would not actually take more than a couple of watts anyways, like not even in the double digit. So even if it gives like 3-4 amps, that's more than sufficient, which it is rated for 6 amps. So it should be more than sufficient. So I did that, and it ended up happening this is what happened. Like it's hard for me to show it properly. Can I align it in a way that the internal shows? It's hard for me to show it, but what happened is that this black ring on the side that you can see, that got caught inside these dents, essentially the serrated teeth inside. So when I put that inside, it captured that plastic, as in the connector, as in the glue part that keeps, or like insulator part that keeps the positive and negative separated, and it kept it in, and when I pulled it out it went in, it stayed in. So this is kind of a dangerous connector. It does not work with normal what do you call that thing, a DC barrel jack. You need a specific one that is 2.5 mm in internal diameter. So it has a lot more complication, like it keeps on adding and adding more complexity inside of it. So this wasn't working. If I connect another one, I haven't connected this one, if I do it, this one will get caught as well, I'll end up breaking this as well. So this also became like a no-go, like I cannot use this as a power source either, like as a DIY buck converter, DC converter, as a power source for this 12 volt, which I was planning to do. So this barrel jack becomes a no-no. You should not use this barrel jack. It's very challenging, it's very weird, and it's poorly thought out, poorly designed, and not tested well enough. That's what I'm gonna say. Now, just because most people are not probably using the PCI lens and PCI cards, full 4 lens, utilizing it, probably that's fine. So that's why it doesn't get caught or didn't get updated or flagged. But now that I have this, my thought was like, okay, what do I do in this case? So I can provide a 12 volt if I go behind it. So this is where the soldering, where this DC barrel jack is connected, and these are its ports, right? As in, this is the ground, this is the positive lead. So I connected this USB-C trigger module, which, if you notice, it has 12 volt marked black. Let me try and show it in a different light. Yes, so you can see that 12 volt is marked black. So this is a 12 volt trigger module, which is nothing but like basically all the different trigger modules have the same design. Is just a particular resistor that is here that tells the IC over here that what the voltage needs to be set, and it is preset. So it is very small module. You can even embed that inside of a cable if you are making a DIY cable out of it. But the baseline premise is that now this one is a 12 volt input that I can serve, and I did, and it works. It works exactly the same way it's supposed to work, and which means my problem is solved, right? Now the PCI should work. Wrong. It does work in certain situations. It doesn't work most of the time, and the reason for that being is, you see, I should open up a browser to show what I mean here. Give me a second for me to open up. Let's go to PCI Express page and let's go to the pinout section. So all these different numbers over here, they are basically the pins. Like, ignore the side, like as in pin 50 or onwards, this side first. Like, let's focus on this side. So this is side A and side B, just means this side A and side B's. Actually, this is side A and this is side B. How can you tell? You see this one particular pin that is short. Let me see, how close can I focus? Okay, yeah, if you can see this, here's one particular pin that is shorter than the others, and if you notice, if you go the other opposite end, the next to last pin is also a little bit shorter. The reason they are done that way, those are called the presence pin. So those ones get connected on when you put it in, those ones get connected last, and those are the ones, that's the mechanism the board used to detect that there's a PCIe card in this slot when those two pins are connected. And what's happening actually is, here this presence pin is actually getting connected to this, and when the voltage of this presence pin is being measured, or you can see there's other ones, there's another one, and there's another one. Fundamentally they're all doing the same thing, but because there's a 4 different presence pin, it's because whether it's a 1-lane card or a 4-lane card or an 8-lane card or a full 16-lane card. So if you are using a GPU, this presence pin will be grounded, not other ones. If the other ones are grounded, the GPU will not work at a full 16-lane capacity. It will be working at a limited bandwidth, right? So the ideal situation is you basically use a mechanism where presence pins are connected, presence 1 are connected to the presence 2 is connected to the interface. But here in this Latepanda's case, what they ended up doing, that they short circuited. Okay, I have probably PDF. So let me zoom it in a little bit. What they have done here, so this is the schematic for the PCIe section. What they have done, they have connected the presence 1 and presence 2, both the presence 2s, because you have to remember this is a 4-lane card. So the card's pin out does have a 1-lane presence and 4-lane presence, both there. You are not supposed to connect them like this, even though during operation they will be connected. You should not connect it like this way. You should connect them to the presence pin from the SoC side, from the upstream side. So the SoC can detect, trying to ask whether this B17 is grounded or floating, or B31 is grounded or floating, and by that it can understand which one is actual length of the PCIe that it should operate at. That's what is usually happening in most of the boards. But here, because they're connected, grounded like this, which is crazy, why somebody would do that, it can only work in two distinct conditions. Either the PCIe card that you're using is stupid enough to not care about, okay, wait, I think I have the audio set up too loud. Let me change that to 16.6. 6 dB. Okay. So now these presence pins are connected in a way they'll only work if the card that you're using does not care or disregards the PCIe lane calculations. So quickly, I'll give you a hint. So this card works. Why? This module completely disregards whether it's like the system is asking whether you work at a 1-lane or 4-lane. It just says yes to everything and then continues to send data over 1-lane. This is a 1-lane PCIe, and this is also a 1-lane PCIe connector. So this one continues to work over 1-lane, even though it says yes to everything. 1-lane or 4-lane, it doesn't matter, right? It just says yes. Whereas this one has implemented the presence pin in the proper way. If you can see very closely, you can understand this, what's happening. You see this connector, the short connector from over here, that is coming and then going back down here and coming down from here to the presence pin. That's what's, so the card is telling that, hey, I am a 1-lane card. The presence 1 will be grounded anyway. So the presence pin, if you presence 2, if you get the first one, if you find it grounded, that means I'm a 1-lane card, operate at that voltage. Challenge is, because even the fourth pin here, the fourth presence, is also connected with all those, so that from the system side, systems can decide whether it's a 1-lane card or a 4-lane card. And PCIe spec dictates, if it cannot figure out, like in that particular situation, it will take the highest length. So basically it will try to operate at 4-lane speed, right? But the problem is, the system that we are working with, this NVMe, this is smart enough, it is on spec. So when the CPU asks, say, hey, I want to talk to you over 4-lane, because you have 4 lane, the NVMe drive says that no, I don't have 4 lanes. I cannot talk to you over 4 lanes. I'm not gonna, like, this seems weird and fishy. I'm not gonna talk to you at all. And it does not work. So this board, because of that reason, does not work with this module. Now, if the pinouts and everything is correct or not, for example, if we bring this module in, we can see something over here. Oh, wait a second. Over here, look, the pinout, both of them, how do I show it? Like this. Yeah, the short on the one side, short pin on the one side, the A side, and then on the B side again, the same, the second to last pins, they are shorted out the same way in both the cases. In one scenario they disregard it, one scenario they don't, and because of that this board would not work with Latte Panda Mu. Even if you give 12 volt, which doesn't matter, because, and this is more important, because this is not even a 12 volt power board. This does not take 12 volt power. It has 3.3 volt power, and let me show you what I mean by that. Is in PCIe spec, not only that you need to give 12 volt, which is these pins, you also need to give the 3.3 volts, including 3.3 volt auxiliary power, which is what, so there should be 1 amps expectation for each of this. So basically it should support 3.3 volt at 3 amps, 4 if you count the auxiliary power, to run the NVMe drive. So the NVMe drive has enough power that it needs from the 3.3 volt, and that's what it operates with. NVMe spec itself does not even, if I remember correctly, let me quickly grab that and verify that as well, it does not even take 12 volt at all. NVMe pinout, let's try and see if we have M.2 spec. Wikipedia is there, maybe. Is there a pinout diagram? No, Wiki does not have it, but there are actually a lot of third-party images. Let's go find one and see it. Okay, so this is, somebody posted it on Reddit, so let's go and check this out. As you can see, in NVMe, the first set of pin, the key that is there, the pins on the right of the key are all power pins. So basically 3.3 volt, 3 of these 3.3 volt pins that we, as we saw, and 3 of the ground pins. That's where the power is sorted out. Rest of the board, it basically uses all the PCIe lanes. No, there are also like other provisions for 3.3 volt powers on the other B side as well. Anyway, so there is no provision for 12 volt. It cannot take 12 volt. NVMe's do not need 12 volt, does not take 12 volt. It's completely pointless to like have that as a holdback. So maybe I should also show it here what is happening. So as you can see, the 12 volts are here, the 3.3 volts are here. They're coming from 2 different sources. And also if we go down to at the end, page down, next page, next one, this one. So this is the case where we can see what's happening in the power section. So this is the DC barrel jack, and this is the USB-C 15 volt PD input. So these diodes are blocking diodes. So these powers can only go in this direction and go this way. It cannot go back and power this section. And this DC barrel jack, however, can power this section and also power this section. But only if this particular circuit over here dictates that only if you have this particular voltage range compliance, then this would run. Otherwise this section would not run. This is just converting it to 12 volt output, like this is a buck converter if I'm not mistaken. So if you have more than 12 volt a little bit, or this is a load switch, I'm not sure if it's a load switch or a buck converter. This should have been a buck converter. That would have been ideal, in which case you wouldn't need this limit at all. You wouldn't need this complicated stuff. Just implement a buck converter over here. Even the 20 volt would power the thing. That could have been one of the simplest steps they could have taken. I don't know why they didn't. This whole thing is pretty stupid to me, or over design under thought. Maybe I should not say something like this, but because somebody worked on this, they have their reasons. But I would like to have a discussion with that person, whoever designed it this way, and have a justification. What the justification is, I would love to know. Anyway, so wait a second. Oh, I see. Cannot change it now, right? So okay, whatever. So the stream is in unlisted mode. I forgot to set it to public, which is why there will be nobody watching this stream today. Should I stop the stream and do it all over again? Maybe, I don't know. I'll change the caption as well for that. Anyways, so that's an idea. Let me quickly finish the chain of thought that I've been having here. So this is the whole fiasco that is happening over here, meaning that's the reason for the 12 volt, why without this the PCIe 12 volt does not work. On the other end, that's also the reason why we don't really need 12 volt at all for this to work, and the reason it was not working is not related to 12 volt, it was related to poor management of that presence pin. And the presence pin poor management is going to be there. I also used a 4-lane card with this, which had more devices on it. So even though it only was operating at 4 lanes, it actually was a 16-lane card, and it worked, but only the first 4 lanes, like first device with it had multiple NVMe drives on it. Only the one NVMe drive worked on it. So that's what is ending up happening. One 4-lane drive device is only gonna work that is compliant with PCI spec, because if it is not PCI spec compliant, like this is not, this just says yes to any kind of presence pin, like 4-lane, 1-lane, 16-lane, doesn't matter. It just says yes and continues to work. And the reason being, it actually does not need even 1 lane. This is much lower bandwidth than that. This is the Wi-Fi 6 card, which operates at a much lower bandwidth than what PCIe can provide. So it doesn't really care which lane count is it. It just says yes and goes in. So in a dumb card like this, it will work, but in a smart form factor where it knows it has to manage whether it's a 1-lane or 4-lane and operate accordingly, because this PCI, this NVMe card can easily break free of 1 lane's bandwidth if provided, like 2 lanes or 4 lanes. It needs to know and operate accordingly. So that's why it's refusing to work. So that all boils down to the poor implementation of this PCIe connector and the power section. The whole thing should be redesigned. Now you must be asking, yeah, well, this is a open source design, why don't you go and fix it? Yeah, it is open source, the source is shared, but there is not a good way of fixing this thing and then going back and sending a pull request and then making it work. And even if I do that, it won't change a thing for all the devices that are already at people's hands. Like I have it here, nothing changes because already manufactured. Most people are using it. Only thing that will change is new people designing their board based on top of this open design after the fix. So I just needed to talk about it just so that I can get it off my chest. It's complicated, it's not for everybody, it's not a topic most people would be interested about or go this deep into the rabbit hole to understand it, and only people who might be interested about it are the people who implemented it or are implementing on top of it. So that's why I just wanted to talk about it. if I can make a short format video or something like that from all my rambling, if I compress it down and make a shorter form video about it, I will. But that's pretty much what I wanted to talk about. So long story short, I need to rethink how do I use this board. My initial intent was to use this 4-lane PCIe for its intended purposes, but seems like that's going to be a challenge for in multiple different ways. So I'll have to figure out what do I do with this. Maybe I will go use the dev board that I have, which is a bigger board I takes from Factor, and operate with that, and let this one just stay as a reference board or something. That's it. So that's the Latte Panda Mu topic. Now next I'll move out to the title that I have for the stream today, which I realize is not something that people have been watching, because nobody's watching because the stream is hidden, it's unlisted. So I'll have to go fix that. I'll have to end the stream and then start it all over again. Thanks for whoever is watching it after the fact, because the video will be available even in the deep dive playlist. So if you're watching it after, hey, hello. But I gotta go restart the stream and start it all over again.